तो स्टूडेंट्स, आज का लेक्चर 07 थर्मोडायनामिक्स का, इस लेक्चर में हम डिस्कस करने जा रहे हैं हीट कैपेसिटी, specific heat of a substance, specific heat for solids and liquids, and specific heat for gases. We are discussing all these things in today's lecture. Now let us start our topic from starting heat capacity by starting heat capacity. Now what is heat capacity? Let us take a container. In this container there is certain amount of substance present. That this is the amount of substance present in the container. These are the molecules of the substance. This is the amount of the substance. Now how much amount of heat is required? I am giving heat to this. Let the temperature of this substance, let this system is at a temperature of, let it's at a temperature of 10 degrees centigrade. If I have to increase its temperature by 1 degree centigrade, means from 10 degrees centigrade, I have to increase its temperature to 11 degrees centigrade. What is 10 degrees centigrade? 0 degrees centigrade is 273 Kelvin. 10 degrees centigrade is 273 plus 10, that is 283 Kelvin. Then 11 degrees centigrade is 284 Kelvin. I have to increase its temperature by 1 degree centigrade or by 1 Kelvin. How much amount of heat is required to increase the temperature of a substance by 1 degree centigrade or by 1 Kelvin? That's called heat capacity. Now heat capacity is the property of a substance which tells us how much amount of heat is required to increase the temperature of the system by 1 degree centigrade or by 1 Kelvin. Therefore, if I represent this heat capacity by letter S, then it is the heat given to the substance to increase its temperature by 1 degree centigrade. That means change in temperature should be 1 degree centigrade, or change in temperature should be 1 Kelvin. What is change in temperature? Initial temperature, final temperature minus initial temperature. Now what's final temperature over here? 11 degrees centigrade. What is initial temperature? It is 10 degrees centigrade. That is, difference in the temperature is 1 degree centigrade. This difference is called del T. Therefore, I will write it Q divided by del T. Now, if del T is equal to 1 degree centigrade or 1 Kelvin, then our S is equal to the Q. That is the amount of heat absorbed required to raise the temperature by 1 degree centigrade or by 1 Kelvin. It will be called as heat capacity. Therefore, we can define it. It is the amount of heat. It is the amount of heat. It is the amount of heat required by the temperature, required by the system to increase its temperature, by 1 degree centigrade or by 1 Kelvin. This is the definition of heat capacity. Heat capacity is then the amount of heat required by the system to increase its temperature by 1 degree centigrade or by 1 Kelvin. Then mathematically, if S represents our heat capacity, it is equal to Q, that's heat given to the system, divided by temperature difference. If this temperature difference is 1 degree centigrade or 1 Kelvin, if del T is equal to 1 Kelvin or 1 degree centigrade, then S is equal to Q, then this definition follows. From this definition we have derived this equation. Now what about the units of specific heat? Units of heat is equal to, SI unit of heat is Joule and SI unit of temperature is Kelvin. Therefore unit of specific heat becomes Joule per Kelvin. Or sometimes we use the unit of heat as calorie and the temperature as degree centigrade. Therefore, unit becomes calorie divided per degree centigrade. This is also the unit. See, specific heat capacity depends upon the amount of heat given to the system, required by the system. That means it depends upon the quantity of the matter present in the system. जितनी ज़्यादा क्वांटिटी होगी उतनी ज़्यादा आपको हीट देनी पड़ेगी 1 डिग्री टेम्परेचर इंक्रीज करने के लिए. Therefore, it depends upon the amount of the system. Hence, heat capacity is an extensive property. It's an extensive property. It's an extensive property. How can we explain that heat capacity is an extensive property? For this, let us take two containers. In one container, there are present, for example, 500 ml of water. In other container, there are present, for example, 5 liters of water. 5 liters means 50,000 ml of water. Now temperature of this system initially let it is 27 degrees centigrade and let it is 27 degrees centigrade. I have to increase its temperature to 28 degrees centigrade. I have to increase the temperature to 28 degrees centigrade. Now I have to increase the temperature of whole substance, that is the heat capacity. Heat capacity is defined for whole substance, for what amount of substance we are given. Now see, here I will require less amount of heat. Here I will require more amount of heat because the amount of the substance is more over here. Therefore, it depends upon the amount of the substance. That's why it's an extensive property. Now, this heat capacity, if we define for solids and liquids, specific heat, if we define for solids and liquids, then it's called heat capacity. Now, second term here comes out to be heat capacity. Heat capacity. It is nothing, it is specific heat. Specific heat of solids and liquids. The only difference is that here we take 1 gram of substance or 1 kilogram of substance. Now in this case what we were doing, we were taking whole amount of substance. When we take heat capacity, we define it for 1 gram of substance or 1 kilogram of substance. Now specific heat of a solid and liquid is defined for 1 gram or 1 kilogram of a substance. Now see how much amount of heat will be required to raise the temperature of 1 gram of substance, means mass here is included. Mass is 1 gram, or 1 kilogram of substance, mass is 1 kilogram. How much amount of heat is required to raise the temperature of 1 gram of substance or 1 kilogram of substance by 1 degree centigrade? That's called heat capacity. Therefore, specific heat of solids and liquids, it's called heat capacity. We denote it by S or C or by any other letter. There are different letters used. Now it is defined amount of heat required to raise the temperature of 1 gram or 1 kilogram of solid or liquid by 1 degree centigrade or by 1 Kelvin. Therefore, what we will do, we will say S is equal to Q, amount of heat required. Temperature difference is 1 degree, that is del T, and mass of the substance is 1 gram, that's M. So the definition gets little bit modified, mass is to be included. Now see, if M is equal to 1 gram, del T is equal to 1 degree centigrade, then S becomes equal to Q. Then the amount of heat absorbed by the system, required by the system to raise the temperature by 1 degree centigrade of 1 gram of substance, that will be called heat capacity. This heat capacity we have defined for solids and liquids. Now in case of gases, we do not deal with the mass of the substance, we deal with the number of moles of substance. In case of gases, we are dealing with the number of moles of substance. Now then, heat capacity of gases. Heat capacity of gases. In case of gases, heat capacity is of two types. In this case, it depends upon number of moles of gas, because in gases we talk about number of moles. Depends on number of moles of gas, that's N, number of moles of gas. Now we have two types of heat capacities in case of gases. Either we bring the heat at constant volume, or we give heat at constant pressure. At constant pressure. In case of gases, this heat capacity is denoted by C. If we define heat capacity at constant volume, then we called it CV, and if we define it at constant pressure, then we will call it as CP. Now see, in case of gases, what is heat capacity? Let us take a gas container. There are gas molecules in it. These are the number of moles of the gas. Let this is 1 mole of the gas. This is the Q amount of heat required to increase its temperature by 1 degree centigrade. Now how much amount of heat is required? For n moles of the gas, for 1 mole of the gas to raise its temperature by 1 degree centigrade, that's called heat capacity of gases. The amount of heat required to raise the temperature of gas molecules of 1 mole of the gas by 1 degree centigrade. That means CV is equal to Q at constant volume divided by N into del T. What's N? N is the number of moles of the gas. If N is equal to 1 mole, del T is equal to 1 degree centigrade, then CV is equal to Q. That's heat absorbed, but heat absorbed at constant volume. Now see, we have already shown that heat absorbed at constant volume is equal to change in internal energy. Since we have already shown in previous lectures, QV is equal to change in internal energy. Therefore, our equation becomes what? CV is equal to del U divided by N del T. Now bring this side. Del U comes out to be equal to CV, or I will write NCV del T. If N is equal to 1, if N is equal to, I'll write it over here. It may not be visible over there. I'll write it over here. Now see, substituting this value of QV over here, I get CV is equal to del U divided by N del T, or del U is equal to NCV del T. This is very important equation. Or if N is equal to 1, that's 1 mole of gas, then how can you define? Del U will be equal to CV del T, or CV will be equal to del U by del T at constant volume. This is very important equation. Remember this equation. Heat capacity at constant volume is equal to change in internal energy with respect to temperature at constant volume. Now at constant pressure, if we define it at constant pressure, then this Q becomes QP, number of moles N into del T. Or I can write QP is equal to CP N del T. If N is equal to 1 mole, then QP is equal to CP del T. Now we have already studied in previous lectures that QP, heat given at constant pressure, is equal to change in enthalpy of the system. Therefore, substituting in equation first, we get, in place of QP we will write del H. Del H is equal to CP del T. Let this is equation first. CP del T, or CP is equal to del H by del T at constant pressure. Therefore, heat capacity at constant pressure is equal to change in enthalpy content of the system with respect to temperature. Now this is all about heat capacity, specific heat of a substance. Now from this lecture, what you have to remember? You have to remember only few equations for your competitive exams. The equations are, you have to remember QP is equal to del H, QV is equal to del U, CV is equal to change in internal energy with respect to temperature at constant volume, CP is equal to change in enthalpy with respect to temperature at constant pressure. Now this thing you have to remember. These questions are as such asked. What is CV? Which of the following is correct? CV, relation of CV with this, relation of CP with this. Now in the last lecture we have seen that del H is equal to del U plus P del V, or del NGRT. We have solved questions over there on this. Now what is del H equal to? Del H is equal to QP. What is del U equal to? It is equal to QV. What is this equal to? Del NGRT. Therefore we came up with new relationship. Qp minus Qv is equal to del Ng RT. You can apply it to chemical reactions where del Ng is the number of moles of gaseous products minus number of moles of gaseous reactants. Thank you for watching this lecture.